dovrebbe essere andato.
Okay, so ready? Sì. Okay, so welcome everybody. Today AJS, Matteo Zanardini from SISSA will present us a seminar about the dynamical optimal transport in spacetimes, the Lorentzian Benamou-Brenier formula.
Thank you, Antonio, for the introduction, and thank you everyone for coming to this seminar. Thank you also for the people online. Okay. As Antonio was saying, today I want to introduce for you the dynamical optimal transport in this kind of spaces that are so-called spacetimes, that are the mathematical model for general relativity. And I will give some attention to the so-called Benamou-Brenier formula, and I will give some bits of it in this kind of setting. This seminar is also based on a joint work that I'm currently doing with my PhD advisor, N.Gigli and F.Rott, which is a postdoc here at SISSA. Okay, the plan of the talk will be, okay. First of all, we start from the basics. We introduce optimal transport theory. Then we give some results in Riemannian manifolds. Then I will move on to Lorentzian manifold, that is spacetimes. And finally, I will introduce the Benamou-Brenier formula in this setting. Okay. Okay, let's start from optimal transport. Optimal transport is a part of mathematical analysis that aims to study how to transport a given distribution of mass into another distribution of mass. As you can see in this picture, with respect to minimizing, with respect to a given cost function. I mean, the easiest possible problem that one can introduce is the so-called Monge problem. You can consider a smooth and dimensional manifold without boundary. Consider two probability measures on it, mu0 and mu1, a given cost function, which is a function of the product space n by m into the negative numbers, which is a so-called cost function. And then you consider this problem in one, which is an infima among all Borel maps that goes from m into m, satisfying this compatibility condition. That is to say, t push forward mu0 is equal to mu1. And you infimize among the integral in mu0, so the first measure, of the cost from going to x, which can be seen as an infinitesimal particle inside the distribution mu0, into tx, which is an infinitesimal particle inside the distribution mu1. Okay, this kind of problem is very difficult to study in this generality because, for instance, it can happen that such Borel maps does not exist. Okay, and I mean, the big issue for this problem is that this constraint is never compact in any reasonable topology, for instance, LP topology, etc. And so you cannot apply direct methods of calculus of variation. I mean, what you can do, very generally, is the main idea in calculus of variation is that to relax the problem to gain compactness. Indeed, instead of infimizing among maps, you infimize among probability measures on the product space n by m, such that the first marginal is mu0 and the second marginal is mu1. And you infimize this double integral cost, where now t of x is replaced by y and integrate with respect to this measure phi. Okay. Now in this setting, which is called the Kantorovich problem, direct method of calculus of variation applies. Instead, this admissibility space of measures, which is the constraint now, is compact in the weak topology of probability measures. And if the cost C is lower semi-continuous, now you can find the minimizer of the problem in two. So direct method of calculus of variation applies. One can check also that the Kantorovich problem is always less or equal than the problem in the Monge problem. Instead, if you have an admissible transfer map, you can consider this measure, identity comma t push forward mu naught, which is now an admissible plan, okay, lies in this set, and it has the same cost. That is to say, the integrand functionals are the same, both in the Monge problem and Kantorovich problem. So we have an inequality between the two. Another very interesting property of the Kantorovich problem is that you can characterize completely what are the optimal plans. That is to say, the probability measures that infimize the problem in two. And it is equivalent for a plan to be optimal to a sort of geometric condition of its support. So optimality only depends on the support on the probability measure, and it is a sort of geometric condition called the cyclical inhomogeneity. Okay. Now let's move to Riemannian manifolds. Okay, what is a Riemannian manifold? I will start from the basics. Okay, is a manifold endowed with a Riemannian metric. Okay, and it's well known that this defines a distance out of it. You can consider any two couple of points, x and y, and you just infimize the length of all smooth curves that joins these 2 points. Just smooth curves from 0, 1 to n. And you infimize the length, which is precisely the integral of the speed scala product with itself, square root of it. Okay, the probability. Okay, this defines the distance. I mean, it's just an infimum. You can check the triangular inequality and so on. But I think what is very interesting in this setting is the Hopf-Riemann theorem, which states that on a given Riemannian manifold, there are 3 notions that are equivalent. The first one is the so-called geodesic completeness of the manifold, that says that more or less that every geodesic you can have in your manifold, the maximal domain of definition is the whole real line. That is to say, if you have a geodesic, you can always find the maximal domain, which is the real line. This is equivalent to the fact that all closed balls are compact with respect to the distance d. This reminds this sort of Heine-Borel theorem. And the third condition, which is equivalent, is that the metric space MB, that is to say the set M endowed with the distance d, defined in this way, is complete. That is to say, Cauchy sequence is complete. These 3 are completely equivalent statements. And okay, if one of these three previous conditions hold, then for every couple of points, you can find a minimizing geodesic. What does it mean? Well, it's just a curve that minimizes the problem in 3. Okay, so that connects x to y, given the points x and y. And moreover, one can prove that it satisfies this sort of condition 4. That is to say, if you compute the distance along the curve, this happens to be affine in some way. The distance from gamma t to gamma s is t minus s, the distance from the given endpoints, or any t and s. Okay, there are some questions? Okay, now we pass to study measures on complete Riemannian manifolds. We can consider this space, P2 of n, which is the space of probability measures that have finite second moment. Is to say, given a point x naught, you can just suppose that the integral of the distance squared from this given point is finite. This choosing a correct point x naught doesn't matter at all, because once you have that such an integral is finite, then it's finite for any other choice of x naught. This follows, for instance, for triangular inequality and Holder inequality, and the fact that we use a probability function. Okay, so what you can do is you can define a distance now on this space that is called the L2 Wasserstein distance. And as you can see, it's precisely the Kantorovich problem with cost equals to distance squared. So you can consider this kind of problem, and this, out of taking a square root, is in such a way that it satisfies the triangle inequality. It defines W2, okay, which is a distance on this space. You can check triangular inequality and so on, blah, blah, blah. Moreover, it's possible to prove that this probability measure with finite second moment endowed with this L2 Wasserstein distance is a complete metric space. But it means that Cauchy sequence is converged. I mean, it's separable because, I mean, M itself was separable. So you can just use density of combination of direct deltas to show that this is actually separable. And it is geodesic metric space. What does it mean, geodesic metric space? Well, it is just the corollary of Hopf-Riemann theorem. It says that for every U0 and U1 belonging to this space, there exists a curve from 0, 1 okay? So you have a curve on measures such that W2 is affine in the same way as before the T. Okay? And this is just a fancy way to denote that this curve on measure connects the the measure mu naught and mu1. Okay, so for every mu naught and mu1 in this kind of spaces, you can find a curve, a measure that connects both and satisfies this. Okay. Then we have another important property, that is to say, if M is a compact Riemannian manifold, notice that compactness for a metric space always implies completeness, so it is always complete. Then, okay, I mean the distance is finite, so the space of probability measure coincides with the space of P2 of M. Moreover, W2 metrizes the weak topology on the space of probability measure. So say the topology in duality with continuous and bounded functions. Okay. Now I want to discuss the Benamou-Brenier formula. Okay. Historically, Benamou and Brenier proposed this kind of formula for because this distance W2 is not very easy to compute, right? It's just a theoretical definition, and there are no easy computations to do. What one can do is that find somehow some equivalent formulation of it, and that is much more suitable for numerical computation. That's precisely what Benamou and Brenier did in their paper, where first introduced this kind of equivalence. But the statement I'm showing now comes from a much more modern approach of it, and comes from N.Gigli and F.Rott. Consider a compact Riemannian manifold and two probability measures on it. Then what happens is that the formula in 6 holds. Is to say the Wasserstein distance, the two Wasserstein distance squared, coincides with an infimum problem where you take an integral from 0, 1 of the scalar product in L2 of mu t of the vector field time dependent vt of x with itself, integrated in the t, where the infima is computed with respect to couples mu t and vt, where t mapped in mu t connects mu naught and mu1, that are the given measures. It is weakly continuous, that is to say, this map is continuous with respect to the weak topology in the target space. Vt is a Borel vector field. Okay. Does it mean for every time you have M that maps in Tn, okay, and this is assumed to be Borel with respect to the topologies. I mean, M has a given topology, manifold topology, and how to connect mu t and vt? Well, is the solution of in the sense of distributions of the continuity equation. We should say in the t of mu t plus the divergence of mu t is equal to 0. Well, this is where distribution means you test with the continuous, it's infinity compactly supported both in time and space. Okay. Now you can wonder what is happening in this kind of problem. You can wonder what is a kind of optimal couple, what can happen. Well, consider mu naught and mu1 to be two probability measures uniformly distributed inside these spheres, these balls in the sphere S2. What happens is that an optimal kind of couple mu t vt is given such that mu t somehow evolves in this kind of dashed lines. And for instance, at time t equals 1/2 is a uniformly distributed measure inside this elliptic shaped figure, because I mean the dashed lines are geodesic, and you know that on the sphere geodesic tend to stay apart from each other and then connect. Okay, and vt are precisely vector fields such that the dashed lines are integral lines with respect to this time-dependent vector field. Okay, this is somehow the geometric picture you should put in mind. Are there questions? Okay. Now I have some remarks. Okay, the first one is that actually the infimum is a minimum, so there exists a way to construct an optimal couple. Okay. The second remark is that you can see from formula 6 that the left-hand side only depends on W2. Okay, so the Wasserstein structure. Rather, the right-hand side only depends on the Riemannian structure, so does not depend on the Wasserstein problem. So you have this beautiful duality with respect to structure, Wasserstein structure measure, and Riemannian structure that is lifted to the space of measures via this continuity equation. Okay. And the last point is that okay, the formula in 6 really resembles the definition of Riemannian distance I gave before, because the distance was given by an infimum of an integral between 0 and 1 of something, of a square root of a scalar product, right? But here now, instead of having the Riemannian scalar product, we have the scalar product in L2 of mu t, of the vector field Vt. And so a possible interpretation is precisely say that P2 of M, endowed with this Wasserstein distance, is an infinite dimensional Riemannian manifold. This is the so-called octocalculus. And the scalar product in L2 of a given measure mu should be considered as the metric tensor in this space. And out of this metric tensor, you can precisely define what should be the tangent space at a given measure mu. Okay, it should be the closure of the gradients of infinitely compactly supported functions. Okay. Questions? Maybe. Yeah, this is the interpretation of out of the formula. Okay. Now I want to move to Lorentzian geometry. Now this was the geometric picture in the Riemannian setting. Now I want to add the time as an intrinsic variable of the manifold and not an evolving parameter like before. Okay. First of all, I want to say what is a spacetime. What is a spacetime? A spacetime is a smooth manifold, typically non-compact, endowed with a Lorentzian metric. So it is a Lorentzian metric. Well, at a given point, you have a matrix in the tangent space, and this matrix have a signature, which is plus, minus, minus, minus. Well, maybe you remember from some course in physics, maybe that the signature convention is usually minus, plus, plus, plus. But I mean, this is equivalent. Just swap a sign, and I prefer the plus, minus, minus convention because of computation gets easier. Okay, and another thing you need to add is a time-like vector field. Okay, I want to precisely say what time-like vector field is. Okay. Suppose you have a given point P inside the manifold, and you look at the tangent space of it. Well, you have now a metric at that point, which has signature plus, minus, minus, and this divides the family of vectors inside this tangent space in three categories. Well, there is the category of tangent, time-like vectors that are the vectors that has strictly positive scalar product with itself. There is the set of null vectors, that is the set of vectors that have zero scalar product with itself. And there are the space-like vectors, that are the vectors that are with strictly negative scalar product with itself. The set of time-like and null vectors is called causal vectors, and this sort of vector produces a sort of double cone inside of the vector space at the level of tangent space. And you can see you have a double cone. One is upper part in the upper part, and one is in the lower part. And I want to discuss what in which way one can distinguish between the two parts of the cone. This is precisely done by the time-like vector. Okay, what does it mean, time-like vector field? It means that you have a vector field. At each point, you return a time-like vector. Okay, so this red kind of vector. Notice, moreover, that given time-like vector field on a space-time is never zero, so it's non-vanishing, because zero, the vector zero is not time-like. Okay, so implicitly you ask for a space-time to have non-vanishing vector fields. So you can see that you have some constraints in the topology. Now, given a time-like vector field, it induces the so-called time orientation. That is to say, you can distinguish between the future and the past. You say that a causal vector is future directed, provided the scalar product with the vector field x is non-negative. So you are in this upper part of the cone. And if the scalar product is non-positive, you say that it is past directed, so it belongs to this down. Okay. The set of future directed causal vectors are called J plus of 0, because J plus cone, J means causal in some sense, and plus means future. Okay, and J minus instead is a set of past directed causal vectors.
Time-like vector field x means for every tangent space G
Precisely. Yes. Yeah. For every point, x at P is a time-like vector that precisely stays in the interior of this cone. It can be both in up or low, okay? But you define what is up and what is low from x. So it's like okay. Now I want to define what is the time separation function. This is done in analogy from the distance function in a Riemannian manifold, when you take 2 points, x and y, and you consider the problem that is the variational problem that supremized among all future directed smooth curves that connects x to y. There are 2 points, x and y, and you have many future directed curves that connect x to y. Okay, of course, okay, if y is not in the future of it, there are no such curves, but let's consider this kind of curves. Okay, and you supremize among all these curves the Lorentzian length. You see now that G is the Lorentzian metric tensor, and that is precisely the Lorentzian length. Okay. I mean, this problem, you can wonder why it is a supremum problem instead of an infimum one, because generally it's an infimum problem, and now it happens to be a supremum. Well, the infimum is always trivial, it's always 0. Okay. What you can do if you have any couple of points and you consider the null, for instance, let's consider the level of tangent space. You want to join x to y with a curve that has 0 Lorentzian length. What you can do is that, okay, project y with the boundary of the cone with a null, with the direction of a null curve, let's say, and then follow just the boundary of the cone, which is composed of vectors, and then you have produced a null curve that connects the point. Because at each point you have a vector that is null. And okay, now this is not smooth, but you know that you can cut the corner. Infimum you get just 0. So infimum problem is always trivial in some sense. The supremum problem is trivial outside a cone-shaped figure out of the first point x, because for instance it can happen that x is here and y is here. There are no such feature directed curve that joins x to y. So it may be that the supremum is attained on an empty set, and so by convention you say minus infinity, and so you get this kind of function, okay, that is intrinsically defined in a given spacetime. This kind of definition produces a so-called causal order. So given 2 points, x and y, you say that x lies in the causal path of y, provided L is non-negative, or equivalently, there exists a future directed causal curve that joins x to y. Okay, this is precisely given a point x. The pictures you should have in mind is to have a future directed cone points out of x that are joined, or can be joined via this kind of curves. Okay. Since now we are considering a supremum problem instead of an infimum one, we don't get a triangular inequality, but a reversed inequality, just because it's a supremum instead of an infimum. And this is the so-called reverse triangular inequality. Given a triplet of points, x is in the causal path of y, the causal path of x, in the causal path of z, then we have that the time separation from x to z is bigger than the time separation from x to y, plus the time separation from 1 to z. So you can have this picture in mind. Okay. Here we can have x, here y, and here it is z. Okay. You can see that you can produce this kind of example where y is in the boundary of the cone of x and z is in the boundary of the cone of y, but z is in the interior of it. So this time separation should be strictly positive, while this should be 0. Okay. So this inequality actually is okay. There are plenty of cases in which it's strictly increasing. And okay, this kind of inequality implies that the causal order is transitive. What does it mean? It means that if you have x in the causal path of y and y in the causal path of z, it implies that the right-hand side is not negative because it was a negative condition, but this implies that the left-hand side now is not negative. And so this is equivalent to us that x is in the causal path. So you always get the transitivity of the causal order. Okay. Now some examples. The first one is the so-called Minkowski space, which is the space of special relativity. Okay. And you precisely compute how much is the time separation between two given points in this space, which is the flat space and out of this metric. Okay. This is precisely the same for as the Euclidean distance. Rather, two things. The first one is that given a point tx, you draw the future cone, another from sy. It lies inside of it this formulation, which has a round kind of section. Okay. This distance now coincides with that square root of time squared minus space squared, which resembles the Euclidean formula. In this case, there is only a plus. There is only a minus instead of a plus. Okay, and minus infinity outside of this cone shape. Well, what you can do to visualize this kind of formula, you take the graph of the modulus of x in n+1 dimensions. Take the graph of this function, modulus of x. Okay, you rotate the graph by 90 degrees. Okay, and you remove the bottom part. So the graph is precisely this kind of concave function, which has infinite derivative when you hit the boundary of the domain, and minus infinity outside. So this kind of function is not Lipschitz continuous near the boundary. Well, the side in the interior is infinity, etc., but on the boundary is non-Lipschitz, and outside of it is minus infinity. Okay, this is an example of spacetime. Well, but there are also examples of spacetimes that have L, the time separation always plus infinity. This is an example of some strange cylinder in somehow you have compactified the time, okay, in such a way you can rotate along this cylinder as many ones as you want, in such a way that if you have x and y, you can always join with a time-like curve, and you can rotate very, very highly in such a way to get an infinite Lorentzian length between the two. And this kind of space is terrible from the viewpoint of causality, because you see that x is in the causal path of y, and y is always in the causal path of x. This is kind of examples, like crazy examples.
So the general area is not necessarily continuous.
Exactly. Yes. Yeah. I mean, it's never continuous, right? Because it's plus infinity in outside the conical region, but
Not necessarily
neither. Yeah. Typically is apex continuous because yeah. But what I'm interested in is somehow to give some topological condition on the manifold and to the metric to get some sort of continuity for the time separation. This is the global hyperbolicity, and it is the strongest possible assumption you can put in the causal ladder of implication of topological assumption on spacetimes. And you require two things. The first one is that the causal order is a partial order. So you have reflexivity, that is to say, every point is in the causal path of itself. You ask for transitivity, which is always true because of reverse triangular equality. And you ask for antisymmetry, that is to say, there are no causal loops. That is to say, if you can connect x to y and you can connect y to x, necessarily x was equal to y. And so you cannot have kind of causal loops. Well, also reflexivity is triggered, right? Because you can always put the constant function, the constant curve in x, and this is causal because the tangent vector is the zero vector, which is with zero scalar product with itself with respect to this matrix. Okay, this is the first condition, and the second condition is that the diamonds are compact. So you can consider any two couple of points, x and y, and you ask that you consider the points in the causal future of x, and you intersect it with the points in the causal past of y, obtaining this kind of diamond-shaped figure. You can imagine this in 3 dimensions. You obtain a kind of diamond shape, and you ask for this to be compact. Okay, this is a condition to ensure global hyperbolicity, and this should resemble the Heine-Borel property somehow. Okay. Now we have bad news for this global hyperbolic spacetime. I mean, typically, the level set of this time separation function are typically non-compact. In Minkowski space are hyperboloids. And there is no analogous version of the Reynolds theorem. That is to say, global hyperbolicity is a completely logically independent statement for time-like geodesic completeness. So there are examples of spacetime that are globally hyperbolic but not complete at the level of geodesy, and vice versa. Okay. But what is true is that under global hyperbolicity, you have a well-posed and compact, in some sense, minimum supremum problem. And so for every couple of points, one in the causal path of each other, there exists a maximizing geodesic connecting the two. Well, maximizing because it was a supremum problem instead of a minimum problem, and satisfying the same property of, let's say, constant speed. That is to say, if you compute the time separation between gamma s and gamma t is equal to t minus s, time separation from the starting point. Notice now that you have to ensure that s is strictly smaller than t, because a posteriori gamma is a causal function, and so if you swap t and s, this quantity is minus infinity, because one is in the past of the other, and typically L is anti-symmetric. It's not symmetric like this. You have to be very careful about the order. Okay, there's some questions. Okay, let's move on. Now I want to give you some good news about these global hyperbolic spacetimes. The first one is that if you consider L maximum 0, as the professor was saying, it is first of all finite, so it does not attain plus infinity as a value. Second of all, is a continuous function with respect to the manifold topology. The second one is the very famous Gerock splitting theorem that says that once you have a global hyperbolic spacetime, you can always find a codimension 1 space-like hypersurface such that the manifold is diffeomorphic to a cylinder over this hypersurface. So like in Minkowski space, you can identify time equal to 0, you find a space-like hypersurface, and the space is diffeomorphic of a cylinder. Notice that it's diffeomorphic, not isometric, so it can oscillate. Okay. Now I want to give you some structural results about causal curves and causal functions. A causal curve is a curve from 0, 1 to n, such that for any couple of times t less or equal than s, you have that gamma t, that is the curve at time t, is always in the causal path of gamma s. There is a function more or less that increases the partial order. These kind of functions are, first of all, continuous almost everywhere. This kind reminds the Lebesgue differentiability theorem for monotone functions, right? You have a monotone curve with respect to some causal order, and it is continuous. And moreover, is also differentiable. Okay, this kind of curves can jump in time. Okay, you have a curve that at some point it jumps. Okay, so this is allowed for this kind of curves. I mean, also, yeah, jumps like counterparts are allowed. Yeah? So you consider also this space, the space LCC of left continuous causal curves, and this can be endowed with a Polish topology. So you have a good space of curve in which you can do calculus of variations and so on. Okay. Okay. Now let's move to causal functions that are more or less the dual of the curves that are functions from m into the real numbers that are increasing the order but in the reverse way. Let's say from given 2 points, x that is in the causal path of y, then you require that phi of x is less or equal than phi of y with respect to real numbers. Okay, So this is a function that increases along the order, but in the vice versa. So of course, that are from real numbers to n, this is from n to n. Well, these functions are always of bounded variation, locally of bounded variation, with respect to the Lorentzian volume measure, and these are always differentiable almost always. This is end and not an implication. Okay, so it actually follows by the property of that function, differentiability. And at each differentiability point, you have the Lorentzian gradient, okay, of this function is always a future directed causal vector. I mean, this function is increasing the order. So you can imagine that the vector of its gradient is always pointing in the future. Okay. Okay. Now let's do some pass to optimal transport in this kind of spaces. What you can do is to introduce another admissibility space for probability measures, and you require probability measures on the product space. You require the first marginal to be 0 and the second marginal to be 1. But you ask also that the plan pi is concentrated on the causal order. What does it mean this? It means that the plan pi is concentrated on points that are in causal order. So you allow only plans that moves points into its causal future. So you allow only particles, in some sense, that are moving into its future. Okay. We introduce also a measure theoretic causal order, which is a causal order but for measures, and you, like in very analogy with what we stated before, is we say that mu0 is in the causal past, the very theoretic sense of mu1, provided this admissibility set is non-empty. Okay. And now, given p between 0 and 1, we can define the p Lorentz Wasserstein distance. Well, distance is not really a distance because it not satisfies the triangular inequality. As we have seen, just L does not satisfy the triangle. This will satisfy the reverse triangle. And you take the supremum, I mean, you take precisely the Kantorovich problem with a supremum instead of an infimum, where the cost function is the time separation raised to the power p. Okay, so you consider another type of Kantorovich problem, and this induces a sort of time separation function at the level of measures. Okay, you can check very easily, very similar to the Riemannian case, that LP satisfies the reverse triangular inequality. And what you can prove is that the set of probability measures with compact support, endowed with this LP and the weak topology, the space of probability measure, is actually globally hyperbolic, in the sense that this less or equal is a partial order in some sense. Okay. And second of all, if you take two measures and you intersect the future of one with the past of the other, you get a compact set in the weak topology. So this property of global hyperbolicity is lifted from the space itself to from the space-time to the set of measures. Well, this is separable, as it was at the beginning, since we consider weak topology, and it is always also causally geodesic complete. It's causally geodesic space. Sorry. What does it mean? Well, precisely at the beginning, instead of considering mu0 and mu1 in P2, we consider it compactly supported, and you ask also that one is in the measure theoretic causal past of the second. Then there exists a curve on measure that is compactly supported. Okay, such that we don't have W2, but we have LP, and we have LP. I mean, as before, we take care of the order just by saying that T is strictly bigger than S, and we can remove also the modulus here. This is strictly positive. Okay.
This generality, you don't know if this has a maximum example.
Okay, using I think you know it. I have to check. I don't remember it by now, but I think that using this compactness, I mean, if you, I think yes. The answer is yes, because of compact support, you can. If L is continuous.
N is compact now. Sorry.
Yeah, yeah. In the assumption, in the general assumption, I don't know. I have to check. But with this compactly supported, it just follows by direct method.
What happens if you take T is greater than or equal to 1?
It does not satisfy the reverse triangle inequality.
Okay.
You have to, yeah. Yes. So yeah, the choice of P is precisely to get a reverse triangle inequality out of it. So you can change the correct inequality for L. You can change the concavity property of the function x to the power P in a real line to get that B, and the supremum, you change these three kind of inequalities to get that P satisfies the reverse triangle. Yes. Yeah, the choice of P is very crucial. You cannot take other powers. For instance, the power greater or equal to 1. Yes, yes, should be like this. Yeah. Okay, now I want to discuss what is Benamou-Brenier formula in this kind of spaces. Okay. Now, first observation is that on spacetimes we don't have an intrinsic distance. Okay, so we don't have a metric space. We need to face the lack of the absolute continuity, since we don't have a distance. But we can find in the monotonicity with respect to this order a powerful alternative. This is the trick, the substantial information. Okay, we consider path on measures, okay, of this kind to be weakly left continuous with respect to topology, with topology, okay, and causal. That means precisely that if S is less or equal than P, then mu S is in the measured theoretic path of mu T. Okay. Say that this kind of paths are left continuous causal paths. Okay. BT would be always a causal Borel vector field. Well, causal means that at each point you have a future directed causal vector at the level of tangent space that fixed at X. And we say that the couple mu T dt satisfies the causal continuity inequality, provided for every infinity causal function, causal means that is increasing the partial order from n to r, we have this formula in 8 folds. Notice that this resembles very much the continuity equation integrated only in space, and the time variable is just considered as for almost every time. Okay, you can multiply by a infinity compact supported function in time, just integrate back, you get also the inequality in time, and there is an inequality instead of an equality. Well, this is very easy to explain why you should have an inequality instead of an equality. Well, because this function is causal, is increasing the causal order. If you take a function that decreases the causal order, well, you should get a negative sign, a lesser equal. So that's why you get greater or equal instead of an equality. And another reason of that is that, monotone function does not satisfy the identity of absolute continuity. The difference of f of x minus f of y is not the integral of the derivative. Well, but you have an inequality out of it. And so it is one of the reasons for which the derivative is greater. Yeah.
Just to be sure, this time is just the parameterization of a curve, and it's unrelated with the time direction of your.
Yeah, where t is at the pedices is always a parameterization.
So when you say integrating in space, you say you integrate
in space time. Absolutely, yes. Mu t is always a measure of an m.
Yeah.
Yes. Okay, there's some other questions. Now, okay, I want to introduce two results. The first is the definition of causal speed that is done by the Oxford paper by Benamou and others. And the second of all, I want to introduce the big thing here. First of all, we require to have a path, a measure that is compactly supported uniformly in time. So say the support of mu t lies in a given compact set K for every time between 0 and 1. What you can define is this kind of formula for the derivative. You take the limit as h going to 0 of LP from mu t to mu t plus h divided by h. And you get the limit from h going to 0. This is well defined for almost every time. And it is the so-called causal speed. Okay. One can prove also that is the maximal L1 function such that the reversed inequality of absolute continuity for every time you are in US is greater than the integral of this sort of derivative. And notice that this is a function from 0, 1 to non-negative real numbers, because this is non-negative by assumption, since ut and ut plus h are in causal order. Okay. The second fact is that we have this beautiful duality for curve on measures and measure on curves. Okay. Once we are given a path, is to say a curve of measures, we can always find a probability measure on the space of less continuous causal curves. They are measure concentrated on curves such that the t marginal, the time t, which for t push over pi, namely, is equal to mu t. So the measure at time t, okay, where et is just the function that from a curve returns the curves at time t. Okay, so we have a sort of set of curves in support of pi. We look at them time t. This is precisely mu t as the. Second of all, we have that this causal speed raised to the power p is precisely equal to the average of the Lorentzian velocities of the curves gamma at time t, averaged with respect to this measure pi. What does it mean? Well, you have this kind of curves. You look at the tangent vector time t. You compute its Lorentzian length, you raise it to the power, and then you get that number. And then you average with respect to pi. And this is precisely equal to the speed at time t for almost every time. Now I want to give you an example. Okay. Consider a global hyperbolic spacetime. X is in the causal path of y, and you can consider this kind of path on probability measure. A fine interpolation between direct deltas. At time 0, you get precisely the delta of x. And at time 1, you get precisely the delta of y. Okay. Notice that this kind of curve, if you put x and y in the real numbers, for instance, n equal to the real numbers, you get that this curve is never W2 absolutely continuous. What happens is that this curve is only weakly continuous and is causal with respect to the partial order in R. Well, you can actually compute precisely what is the admissible set between the margin, the measure at time s and the measure at time t. Well, it's just a singleton. You can solve a linear system, for instance, and you get precisely that this is a combination of direct deltas computed on couples, where the couples are always in the order, because x to y was an assumption, and xx and yy are in the order because of reflexivity. Okay, so the supremum problem of LP is just computed on a singleton, and you can precisely compute that LP between US and UT typically is as this P root of T minus S shape. Okay, so it's a P root. Okay. And you can compute what is the lifting measure out of this curve, and this is precisely the uniformly distributed measure on this set of gamma epsilon curves. You have this curve gamma epsilon and labeled with epsilon between 0 and 1, and you take the uniformly distributed measure on this set of curves, where the curves gamma epsilon, the curve gamma epsilon is defined to be the left continuous causal curve that jumps instantaneously from x to y at time t equals epsilon. So you have this kind of uniformly distributed measure on curves that jumps from x to y at all possible times. And these are, of course, left continuous because x is in the causal path of y. Okay. Just some questions about this example. Well, you can check very easily that this kind of plan satisfies the point 1 and the point 2. Okay. This is a p root, so you can compute the limit precisely when this is 0. And also the curves jump from, were constant. I mean, at least at parameter t equals epsilon. So also this other integral is 0, so t almost every time. And also this holds very easily. You can push forward. Okay. And now I want to present you now what is the Benamou-Brenier formula in this setting. Okay. So given a global hyperbolic spacetime, we consider P between 0 and 1. We take two probability measures with compact support in M. Then what happens is that this kind of LP, which is the P Lorentz-Wasserstein distance, is equal to a supremum or of a Lorentzian type of scalar product in a sort of integrated sense with respect to Ut, where G is the metric tensor M, of these time-dependent vector fields raised to the power P half. Okay, and the supremum is computed in some sort of set of couples mu T of Dt, where P mapped in mu T is a left continuous causal path that connects mu naught to mu 1, such that the support of this measure is uniformly supported in a compact set uniformly in time. Bt are causal Borel vector fields, and the causal continuity inequality holds. So you require only for some inequalities instead of equalities inside of the admissibility set. Okay. What does it mean?
So instead of saying continuity equality,
yes,
we say continuity equality. The conclusion is
it can be empty set. It can be the empty set. Yes. So it's no. The answer is no. Yeah, okay. Now I managed to make a proof, but maybe for time reasons I will skip it, and I will show to you what is precisely this theorem in the previous example. Okay.
Can you show me again the definition of
Okay. For every causal function, C infinity, so a function that increases the causal order, you have this kind of inequality. The derivative in time of the integrated phi dt minus the differential of phi acting on the vector field dt integrated in ut is non-negative.
if you set an infinity equal to 0, this would be empty.
Could be empty for any, yeah. If you require it for any phi to be equality, this can be absolutely empty. Yes. I mean, I can characterize if equality holds, then some special condition for the measures holds, like the plan is concentrated on smooth curves. I mean, in the previous case, in the example, the lifted plan was concentrated on jumping curves, and so some sort of derivative passing under the sign of the integral does not hold. So is a true inequality, not an equality for every phi. What happens actually in this example is that the vector field, optimal somehow of this choice, is the vector field 0 for every x. Actually, this kind of curves in the lifted plan have 0 speed for almost every time. And what happens is that so the second addend in a causal continuity inequality is 0, and the first addend is actually computable, and you can actually compute the integral of phi mu t, which is precisely this affine function in t. Okay, You can just take the derivative, and this is phi of y minus phi of x. And you can show that, okay, this cannot be always 0. This is non-negative because phi was causal and x was in the causal past of y. So this inequality is true because of the set of functions in which you were taking the integral, okay? So this is the proof of the causal continuous inequality in this case, right? I think I will stop here. Thank you.
So, is there any other questions?
Yes, I mean, this leads for sure a sort of Lorentzian orthocalculus.
Don't you think of this P2 also PP with some
Yeah, kind of this, yes. Because the formula actually says this, right? Is very similar to the formula. You can say that this is actually a time separation of an infinite dimensional space. You're just taking the supremum of some integral in time, okay? Where this should be the scalar product you put at the level of tangent space. Yes. This can be one yeah, or yeah. This can be an application. Also, it connects to from the static viewpoint of the transportation problem to the dynamical one. So like
standard case,
okay.
Something similar is this. This is related to orthocalculus. So it's smaller.
I think it's absolutely true. With the
Same or just I mean, I'm not sure this the same.
the triangle comparison sense.
Yes, triangle comparison sense.
Yeah,
I don't know from below by 0 or from above by 0. I don't know which one.
I mean, okay. In this Lorentzian business, signs are always opposite, so I should expect the opposite.
Sorry, maybe 0.
Yes. Yeah, this space should be cut 0. But this, I think, can be proven without the Benamou-Brenier form. Actually, I think via some sort of gluing method, you can prove it. Yeah. I had a look on this some days ago, and I think, yeah, of course. And it should be independent on the Benamou-Brenier formula. You can do it via gluing. I mean, it's very easy. Yes, yeah.
The question is related to my previous one. Do you know what happens in the limit where P approaches 1? Like I understand for P larger than 1, it's the reverse triangle inequality breaks, but it would be nice to say, okay, there's a vector field on the finite vector field with no time parameter that describe the sort of.
I don't know. Maybe I never checked actually if okay, if P is 0, I mean everything trivializes because yeah. If P is 1, I don't know if there is something that breaks down in the proof. I really need to check. Maybe it's true. I don't know. In the Riemannian setting, it also for P equal 1. Maybe it's a delicate case. Oh, for sure, you have some non-uniqueness business. Maybe P's when it's between 0 and 1, you have a strictly concave function, so you can manage to have uniqueness properties of the
I
transport.
mean, I think in the Riemannian case, you can solve the non-uniqueness by asking for the to be unique.
Just be.
Yes, and this integration just have a unique.
Yeah, this is very tricky because in here I'm allowing transport along null vectors, null direction. So unit speed is impossible. because you allow zero speed here.
Sorry to interrupt the discussion, but there is a lecture. So
yeah, so okay. Okay. Thank you, Marco. Bye bye.